Okay, thanks everybody for coming out today. We're really excited to have Jeff Heer here interviewing for both CSE and the iSchool. I'll keep the introduction short and just give you the one trivia fact. So Jeff is the only grad student to have won both the IBM Research Fellowship and the Microsoft Research Fellowship. And in case you're thinking that's a good goal to set for yourself, they actually changed the rules after he won both of them. And so he will remain the only student to have won both of them. And with that, I'll give you Jeff.
Great. So thanks, James. So as James said, I'm Jeff Heer from UC Berkeley. I'm happy to be here today at Washington to share with you my research on interactive visualization. And I'd like to start my talk with an example. So imagine a colleague of yours is running a simulation, generating lots of data, and comes and asks you for help making sense of what they're collecting. So it's always good practice to first inspect the raw numbers. So you might eyeball the data and get a sense of, for example, maybe the range of values involved. Or here you might notice, say, set D has a lot of repeated values. But other than that, it might be hard to see what interesting patterns might lie in the data. So of course, a common approach for sense making here is to run some statistics. In this case, we might notice, interestingly enough, both columns seem to have the same standard, mean and standard deviation across data sets. And if you think, well, maybe a line would describe this data well, you notice that the same line describes each data set equally well. Well, that's interesting. But of course, if we plot the data, immediately we get more insight into what the unique patterns behind each data set might be, ones that often elude simple statistics. So the lesson here is that through an appropriate visual encoding, we can leverage human visual processing to more rapidly get insight into data and then hopefully benefit our analysis process. But of course, these are some contrived examples. I'm showing you 10 tuples of 4 data sets. And the real-world data sets generated in both research and industry tend to be much larger and often have a more complicated structure. And so the goal of my research in interactive visualization has been to define interactive visual representations of information with the overarching goal of allowing us as humans to more effectively analyze and communicate information. And so in my talk today, I'd like to share with you 3 interconnected strands of research I've explored in my years in graduate school. And the first area I'd like to share with you today is visualization techniques. That is, new visual designs or new encoding algorithms or interaction techniques that help us more effectively understand and communicate data. I've also looked at ways of generalizing these techniques into software infrastructures, that is, creating toolkits that help programmers more effectively create and customize novel visualizations. We've then taken these techniques and these tools to create new types of analysis environments, with a particular focus on supporting collaboration. So how can teams of people collectively ask questions of data, formulate hypotheses, and marshal evidence? And so I'll be talking about each of these areas in turn, starting again with visualization techniques. And I'd like to briefly share with you techniques for 3 different types of data that you might encounter. And the first is hierarchical data. Now, hierarchies or trees are, of course, a very common data structure in computer science, biology, and in any number of other fields. So in this case, imagine we have an ontology of 10,000 nodes, and we'd like to explore it, get a sense of the data involved. So one approach we might take is to visualize that structure. And so here's one approach that's made available to us by Microsoft. So as you can see here, the tree is represented in an indented fashion. So depth and breadth are linearized, and this can help have a nice aspect ratio to use this as a component along with other interface widgets. But it also has some problems. It might do all right at helping us find individual elements, but as soon as we want to get a sense of larger structure or compare different parts of the tree, we can see already a massive degree of scrolling may be involved. And of course, as we scroll, we might find that additional view navigation becomes necessary. Now, of course, there are other representations we might choose. For example, the classic layout algorithm due to Reingold and Tilford separates the breadth and depth of the tree along different spatial dimensions. And so here we can get a much clearer structure of the branching patterns within the tree, but you may have noticed that to do so, we've already zoomed out, and in this case to the point where we can no longer even read the text labels, or the text labels themselves being probably one of the most important things we need to effectively navigate the structure. Of course, if we want to expand the tree further, this problem gets more acute. And if we continue this process, it turns out we can actually render the tree using a very efficient approximation. So to deal with this problem, Stu Card at Park and I came up with a technique we call degree of interest trees. And the basic idea we had was, can we constrain the exponential growth of the breadth of the trees, limiting it to the available screen space? And so to do that, we realized the important question is not only how do you show the information, but what information to show. So what we do is behind the scenes create estimates of the user's interests across the different parts of the tree. And these estimates may be based on input from the user, such as mouse clicks or search queries. And the goal is to then use this distribution of interests to figure out what parts of the tree to filter and aggregate and thus limit the presentation. The result being an attention-reactive, space-constrained layout. So let me make this a little bit more concrete by giving you a demo. So this is the degree of interest tree, again, showing this 10,000 node ontology I mentioned earlier. So by start, I haven't clicked anything, so it assumes I'm interested in the root of the tree and then propagates some interest down 2 levels to show some branches. Now let's say I'm interested in places, particularly stars, so I might click celestial here under places. Then the tree expands and what I clicked becomes a center of interest, and again, interest is propagated both up and down the tree structure. Perhaps I'm interested in constellations, so I click that and it expands. You see I got a breadcrumb trail as I run out of depth here. And then I have an ordered list of constellations. Now I run out of space, but I have aggregated results at the end. So I can click that, redistribute interest behind the scenes, and then page through the data that way. Of course, if I change the layout by, say, giving it more room, it will automatically adjust the layout to take advantage of the screen space that's there. Now I can also do this for multiple foci. So for example, let's say I search for a term, say the word visual. By default, you might notice these 2 triangles have highlighted in red. So I could navigate down those trees manually and find those results. Or I could change how interest is distributed throughout the structure. In this case, making all search hits interesting and propagating the interest through that. Now this kind of leads to an explosion here. And of course, I could pan the view to pop through and see where different results might lie. But that might be tedious, so another approach is again to change the interest distribution. In this case, showing only interesting nodes and their immediate ancestors up to the root. This helps a bit in removing clutter, but we still have problems with depth. So we could take this even further if we wanted to. In this case, propagating interest only through the tree of least common ancestors, thus providing a semantically zoomed out view where we might find different search hits of interest, perhaps select one, and then zoom back into a more standard view of the tree. In this case, I can now explore my interests, say, in design and architecture. We'll close that. So that's one example of a visualization technique, in this case for hierarchical data. Next, I'd like to talk about a very common type of data, which is tabular data, in particular time series. And in many cases, mundane, even simple graphics are often the best way of communicating this information. So this is a line chart showing atmospheric carbon dioxide measurements over 3 decades. And so just looking at this chart, a number of interesting trends are already apparent. One is that each year you can see there's an oscillation in carbon dioxide values. The other is that you can see over the decades the rise in CO2 is not only going up, it's accelerating. There's a bend or a convexity in the curve that suggests those rates are going up at a fast rate of change. Now, doing this, we've made one explicit visual encoding decision. That is, we chose to use a line chart. Now there's many other visual encoding decisions you might make, some of which are implicit. One here that we can adjust but might not have thought about is the aspect ratio at which the chart is plotted. So here's the same data, almost the same chart, but plotted at a different aspect ratio. And this is useful because we can see different things. This bottom chart is not as good as seeing the low frequency trend. That convexity is not apparent. However, we can see the individual yearly oscillations much more clearly. So let me do a call out. And you can see that for each year, there's a more gradual rise and a steeper decline in the CO2 levels. And it turns out this is tied to patterns of foliage in the northern hemisphere, which is where the majority of plant growth on the Earth lies. And so one of the takeaways we had from this is that, how could we optimally choose a set of aspect ratios to present different trends in the data to a user? So this led us to investigate techniques for aspect ratio optimization. Now, we know from perceptual studies that the human eye and the visual system is very attentive to orientation of line segments. So one approach to choose an aspect ratio is to try and maximize perceptual discriminability of line segment angles. Basically, take the line segments in a chart and try to make them maximally different so that you'll notice be more likely to notice differences in slope. So one way to do this is through iterative optimization. So this is one global objective we could apply. In this case, looks at all pairs of line segments and tries to find the aspect ratio that maximizes the difference in orientation. If we take this and we apply it to the data set directly, we end up with the bottom chart here. It kind of is preferentially weighted to high frequency data because it's looking at every individual line segment. So that's why we get that nice separation in slopes for each year. However, we'd also like to capture the case where there's other, perhaps lower frequency trends. So I won't go into all the details of our algorithm, but I'll sketch out what we do. We take the Fourier transform and look at the frequency domain of the signal, look for peaks in that to suggest potential trends, and then use those peaks to generate, through low-pass filtering, trend lines, here shown in red, which we can then also run through the same aspect ratio optimization. So why are we doing all this? At the end of the day, we get a collection of aspect ratios that display software that can then suggest to a user. So there may be different trends within the data that one might miss. And so we can have the software recommend additional views of the data to hopefully maximize the amount of insight we're getting. So there was an example of hierarchical data, now an example of time series data. Of course, there are many other types of data we might encounter in the wild, some of which even may be relevant to current events. So, for example, what can visualization tell us about this guy? This is, of course, Ken Lay, the former CEO of Enron. So back in March of 2003, the United States Federal Energy Regulatory Commission released over 1.5 million internal emails from the Enron Corporation. And so we thought this could be an interesting use case for visualization, in this case, of the Enron email corpus. Now, as you might expect, many of these emails are mundane about things like who's going to lunch with who, or passing around really jokes I shouldn't repeat here. But for the rest, perhaps we can learn something about corporate malfeasance. So we built a visual analysis tool for email archives. And this is a prototype we built. And the main display you see here left is not like a smashed peacock. It's actually a social network of employees inside the Enron Corporation. And a link is being made between employees if they've exchanged email traffic. And so, in addition to the social network, you can click on a person or a link and get access to all the email communication either by that person or between the pair. In addition, we've coupled that with a number of filtering and search options, for example, by connectivity, so filtering based on how many emails people have exchanged, as well as a timeline showing the email traffic over time, but also allowing us to filter down to particular time regions. And then keyword search that then shows the results in colors, including overlap. So here we've searched for the terms California and for the term FERC, which stands for Federal Energy Regulatory Commission, to hopefully highlight people who may have been involved in manipulating California's energy market. So then we can zoom in on interesting clusters, particularly those of high connectivity. In this case, this is a zoomed in view, and look at people's email traffic and try and get a sense of what they were talking about. Now, we use this tool and we filter down into what we thought were power players, people with high email connectivity around these terms. And doing that, we found John Shelk. So looking at his email, he jumped out. He was a Washington lobbyist who was issuing reports, basically minutes from congressional meetings, that he would then send back to these other players in Enron. So then we wanted to follow his email trail and look at the different people he was talking to and see if we can uncover anything interesting. And as we did this, it led us to Tim Belden, who is a bit of an anomaly. So here I've clicked him in the interface, which is why he shows up in white, so he's highlighted. And what was interesting about Tim compared to others was that while he was also getting high-level email traffic from John Shelk as well as others, it was unclear to us what he was doing with it. While others would reply or forward emails along, so we got a sense of bidirectional traffic. With Tim, things just seemed to disappear. So we didn't know what he was doing with all this information he was collecting. So we highlighted him and thought, well, he might be an interesting person to interview, perhaps an informant. Of course, we had the benefit of having done this analysis after there was already an extensive federal investigation. So we simply typed his name into Google, and lo and behold, found that he was actually the mastermind behind manipulating the California energy market. And so from this particular example, I took 2 lessons. And so one is that while visualizations might not always give us the exact answer, they are incredibly powerful tools at helping us ask smarter questions more quickly. The second lesson I got was that if there are interesting data sets, get them as quickly as you can so you can ask those questions before somebody else does. So those are 3 examples of visualization techniques we developed in our work at Berkeley and at Park. And of course, there's been many different visualization techniques. In fact, people have been looking at this now for about 2 decades. And so when I started graduate school, I was very excited about the topic of visualization, but given some of the interesting techniques that have been developed, I wondered why they didn't have more widespread deployment. While some of these are economic issues, I also found a couple of technical issues. So what were some of the setbacks to adoption? One that I found was that visualizations are hard to create. So for instance, the initial implementation of the degree of interest tree, which we did from scratch, required a lot of development. It took a lot of time and a lot of skill for things like data management, layout and encoding, rendering, animation, interaction. But a lot of this was reinventing the wheel. Like, why can't I just focus on interest estimation and layout, which were the novel parts of the algorithm? The second setback to adoption was that pre-built widgets aren't enough. So a number of other researchers have built component libraries that allow you to take a pre-built visualization widget and tie it up to data. Now this is great. It makes visualization more accessible than it would be otherwise, but it also makes customization and coming up with new designs difficult. You still have to start from scratch. And so I realized that good designs are often tailored to application domains which have their own conventions and semantics. And this suggested a toolkit approach. How could we build tools that will more effectively help people create new visualizations or customize them to their own domains? And so this led to my work building 2 different visualization toolkits. The first was my master's work at Berkeley as a Java-based toolkit named Prefuse, and we've recently followed that up with a set of tools we built in Flash, a toolkit we called Flare. But both of these follow the same overarching design patterns. That is, you start with raw data and you need some sort of language for data transformation and data input to then load data into in-memory databases that you can manipulate. You then need a way of mapping that data into visual structures. That is, taking attributes of your data and mapping them into variables such as position, size, shape, and color to effectively convey that information visually. Then given that geometric abstraction, you then of course need techniques for rendering that view and then providing interaction that allows users to feed back into any part of this pipeline. And so in building these tools, we built a set of software modules addressing each part of this pipeline. And in particular, one of the main contributions was an extensible set of operators for defining visual encoding. So that's mapping from data tables to visual structures. And so I'd like to now give you a quick demo of one of the toolkits to give you an idea of what it's like to use it. So this is a set of visualizations I'm going to show were built in the Flare toolkit for Flash that we recently built. The data is fake. I'm not trying to teach you anything interesting about the data, but rather illustrate some of the features of the underlying tools. And so this is a visualization here of a tree. And what you see on the left is some markup language that actually defines the visualization. So here's a set of operators, that is, that define the visual encodings that map the data to visual form. And then here under controls, some different interaction techniques you can apply. Now, you can write visualizations directly in code, or you can also use markup language like this in frameworks such as Adobe Flex to write these things declaratively. So for example, because I put these 2 controls in here, I have a panning and zooming control for exploring the data that way, and also an expand collapse control for expanding tree branches or collapsing them. I can also reset this view. And because we have this operator framework that defines visualizations, one of the nice side effects is that we can make changes to the visual encodings at runtime. Simple examples include just changing the layout. So from going from this top to bottom node link diagram to, say, using a force-directed layout, here using a physics simulation with spring embedding to kind of use forces to lay out the tree. Now, as other layout algorithms are possible, so for example, laying things out in polar coordinates to get a radial layout, or even using that old standby, the indented tree layout. In this case, though, notice that all the same interactive controls still work across these different representations. If I was clustering data, I might instead want to use a dendrogram layout, and here I'll hide the nodes. So you get a nice flexibility of being able to look at data in different ways. And of course, this isn't limited just to layout. For here an example, I'll go to a radial layout, but change the shapes, hide the edges, and end up with what's called a radial space-filling layout. So here we're using adjacency and layering to communicate the hierarchical structure. And again, our input techniques still work as before. Now, of course, this is mainly focused on the tree structure of the data. Imagine this tree actually represented an organizational chart, in which case we might have multivariate data about each node, including someone's name, how long they were with the company, maybe what their salary was, who knows. So we could take those other variables and, of course, make them subject to visual encoding instead. So here I can use axis layouts and size, shape, and color encoders to encode the data in a different form. And again, because I have this operator framework, I can change it on the fly. So I can maybe add a distortion technique plus an interactor. So maybe if I have cluttered data, I can zoom in and break it up in this way. Perhaps more interestingly and more usefully, I can also change the parameters of the operators. So for example, going from a linear scale to a log scale or back again. And so here I'm just trying to demonstrate some of the flexibility you have and how simple it becomes to build visualizations using this approach. So going back to the slides. So we've been very happy with the results so far. We've developed these toolkits. We've evaluated them through both user studies and through real-world deployment. And so both of these have been released as open source projects, which collectively have now been downloaded over 50,000 times. It's been a lot of uptake within the visualization community, and it's been used by students and researchers in both industry and academia. And in addition to the software artifacts, we wanted to make the design decisions we made be able to be reapplied in new contexts. So we also described our architectural choices as software design patterns so that others could take them up and reapply them in new domains or new platforms. But perhaps the most rewarding part of building these tools is the rich collection of visualizations that have been able to be built by both myself and others, a number of which have led to publications in top-tier venues such as ACM Chi and IEEE Infoviz. So for example, Don-Tom Fon and Pat Hanrahan at Stanford used Prefuse to build new algorithms for flow map layouts. Chris Collins at Toronto used it to visualize WordNet data in what he called docubursts, and this was featured in the Toronto Star, which is Canada's highest circulated daily. Adam Pereira and Ben Schneiderman have built new social network analysis tools, which have led to a string of publications. And others at Toronto have used Prefuse and extended it to show connections between related visualizations of the same data in a system they called VisLink. Now, of course, all these examples have come from the visualization community. Other communities have picked this up as well, including in bioinformatics. So this is a figure from the Gene Biology Journal that shows relationships between gene expression and gene function. And in the Bioinformatics Journal, this was a system for showing cellular interaction pathways segmented by different cell regions. And so overall, we've been very pleased with the uptake of these tools that have allowed not only us to build new visualizations, but put the hands in others, domain experts, who can design visualizations for themselves for their own data. And that's one of the great things about building these tools and having these techniques, is that we can get beyond the nuts and bolts of building visualizations and really, again, focus on the higher level goals of supporting analysis and communication. And so in doing that, we've built a number of new analysis environments, and they've really highlighted for us an interesting area that hasn't been received as much treatment within the visualization community, which is collaborative visualization. And so I'd like to start this section of the talk by telling you a story, basically, of how we arrived at this research topic. And that's a tale of two visualizations. The first visualization I'd like to share with you is Vizter. So before MySpace and Facebook were even launched, there was a website you may have heard of called Friendster.com, which was the first to amass over 1 million users and really kind of kick off at a large scale the social networking phenomenon. And so interested in this new development, my colleague Dana Boyd and I, back in, let's say, early 2003, scraped 1.5 million Friendster profiles off their service. We're analyzing it, and among other things, built an end-user-centered visualization to allow users to explore their own online communities. So let me jump into the demo. So Vizter was based around what we call an egocentric social network. So you expand people's networks in a piecewise fashion. So I could double-click anyone in the network and start expanding theirs as well, and I could explore communities. I use a force-directed layout to position the nodes. This kind of helps show community structures fairly well. And we let it run in the background to give a playful nature that matched well the behaviors we saw of people using this service. But in addition, we wanted to create a playful tool, but one that was also informative. So we tried to sneak in, as it were, a bunch of analysis features to allow people to explore their networks more deeply. So for example, there's an X-ray metaphor for you color the nodes to show different profile attributes. Here using color to encode popularity. So the purple people are the ones with the most friends in the network. Or to look at gender or relationship status, find out who's single, who's not. So if you're looking for someone single who shares your interest in philosophy, you can go ahead and click that in the profile. We index all the profile text so you can search that as well. But you might not be surprised to learn that, given your love of philosophy, sadly, snowboarding is still more popular. So we can turn that off. So people had some fun with that, but perhaps most interesting was people's reaction to another feature, which was automated community analysis. So I'm going to click this button. And my computer's going to thrash for a second, and there we go. So what we've done is behind the scenes, we've run a hierarchical agglomerative clustering algorithm, which at each step tries to maximize linkage between clusters while maximize linkage within clusters while minimizing linkage between them. And the result, it picks the optimal value of that objective function and then shows the results as inferred communities. Now, of course, these data mining techniques aren't always perfect. The graph may be missing real-life connections, and social data is often inherently messy. So we wanted to give users some feedback into this process. So at the very least, what we did was provide this slider here that, as you adjust it, changes the community groupings. And what you're actually doing is changing the slice through the resulting cluster tree to explore different outputs of the clustering technique. Interestingly enough, people played with this, would move this slider back and forth. We'd find that they'd find something that looks right to them. And after doing that process, then comment to us about how smart our algorithm was. So it's still a nice marriage of data mining and human sense making. And so we deployed this visualization in public settings. So that when it had a large displayed, projected screen like this, as well as an interactive kiosk, and observed people use it. And this resulted in a number of interesting observations. And the one I want to share with you today is that we found that groups of people spent much more time in front of the visualization than individuals. And as we observed this, we realized it was in part due to the conversations they were having. So people would challenge each other to find things in this data, like find paths between one friend or another, particularly ones who didn't like each other, so which ones bridge them. And also to probe community boundaries, so how do college friends interact with people in the music scene, etc. And interestingly, people also went about challenging reported information. People engaged in data verification. And my favorite quote to this effect was, "What? She's not single?" Which happened more than once. But at the end of the day, what we noticed here was that social play, in this case, was resulting in informal analysis. And so we asked the question, how could we better design user interfaces to both catalyze and help capture some of the insights that are being generated in this process? And it was at the time we began asking those questions that our attention was brought to another visualization. So it's the second in my tale, which is the baby name Voyager, which was an online applet written by my colleague Martin Wattenberg at IBM Research. So how many people of you are familiar with the baby name Voyager? So about half the room. So this is an interactive applet that was placed on the web that allows you to see the popularity of baby names. So Martin's wife Laura wrote a book to help expectant parents choose names for their children, and in the process collected 120 years of data from the Social Security Administration. And so this resulting visualization, which is like an interactive figure for the book, shows the popularity of baby names as width and how it changes over time. And so Martin released this visualization into the wild and became kind of stunned by its success. It's basically the analogy of a hit song in terms of internet memes. And what really surprised him is as he did vanity searches for this on Google, he found all these blogs talking about activity showing very similar patterns to what we saw in Visitor. So people forming hypotheses, finding interesting observations. So for one example is this. This is all names that begin with the letter A. And you'll notice that there's a dip here around 1940, 1950. Here's E. Here's I. Here's O. So apparently vowels used to be cool. And then, but they're making a comeback, so don't worry about them. But what was interesting about this example is, and again, I don't know the answer to why this might be. One person said the name Adolf caused it, and then it spread to all the other vowels. I don't know about that. But so if you know the answer, come tell me afterwards. But regardless, what was interesting was that Martin had played with this data in its raw form and in different visualizations, never even noticed this pattern. But by putting it out on the web, he was able to kind of leverage collective intelligence, if you will, to point out some of these interesting patterns. And so this led to the research thesis I've been exploring more recently in my PhD research, which is this idea of social data analysis. So visual sense making can be social as well as cognitive. And while I've been looking in here, showing examples of informal domains, this is of course true in more formal domains such as business intelligence, scientific collaboration, and intelligence analysis. And so my goal was to ask, how can user interfaces better support and encourage these forms of collaborative analysis? And the approach I've taken to try and answer this question is to understand the impact of our user interface and visualization designs by building and deploying real systems. So these are systems that are out there getting real usage. And so I'd like to share with you one of the systems we built. This was a collaboration with Martin and Fernanda Villegas at IBM Research. It's a system I built called Census. It's a web application for collaborative visualization of 150 years of United States Census data. So you would come to this website, and there'd be a number of different displayed featured visualizations. And they had different data sets of US Census data, for example, occupation data, immigration data, other demographic variables, tied to interactive collaborative visualizations. So let's jump into a demo. This is the job Voyager. It shows the makeup of the US labor force over the last century and a half, and can be searched in many different ways. So for example, we can mouse over the visualization and look at different trends. This is normalized data, so you're seeing the percentage of the workforce in that occupation, or at least reported workforce, in that decade. So one thing that jumps out right away is that farming. So you see that it was once very big and then died out. So here you can click it, zoom in, and get a clearer picture. But as I've done that, you might have noticed that this comment popped up on the side as well. So this was a comment left behind by someone who came to this view, and he said, "There's no arbitrary division of labor between men and women on a farm. So unless there are millions of bachelor farmers, these numbers have more to do with the prejudices of the folks in charge of the data than with the populations of American farms." So in this case, the commenter's beef is that there's a very small sliver of women counted as farmers, and yet farm labor tends to be distributed amongst a family. So are women who live on farms not being counted? That's what the questioner is asking. And indeed, we saw lots of comments like that where people had some sort of insight or maybe suspected bias in how data was collected and planted signposts in the data to help point that out. Now there's other analyses we could run as well. So for example, we could filter by gender. So here we see just the picture of women in the labor force. And so you see a comment here pointing out that there was a very large increase of women in the labor force after World War II, so from 1950 to 1960. And in this case, the commenter used drawing tools we provided to provide annotations on the graph to disambiguate the trend it was they were referring to. And here another commenter points out, perhaps interestingly, that household workers actually had the reverse trend. So that as women have gone up in the labor force, the number of people reported at least as household workers has dropped. Now, another way we could try and explore data is by typing in queries. So for example, if I type in the letter B, I get all jobs that have a word that begin with the letter B. Now, as I do this, I'd like you to watch the location bar along the top here. So I go B, B-A, B-A-R. And you'll notice that as I type, this updates in real time. And while this seems like a somewhat minor design decision, it was actually something we very consciously did to support sharing and collaboration, not just within the site, but across services. So at any point, you could grab this URL and instant message it, email it, blog it, and someone could come and see the exact same thing that you're seeing, thus forming common ground for conversation. One nice side effect is that by tying into the browser's history, we actually got the back button to work right, which I wish more AJAX applications would do. But perhaps even more importantly, if you type one more letter, you get to one of my favorite trends in the data, which is bartenders, which no one wanted to admit to being in 1930. So yeah, let's zoom out. So one other example I like to show, I type M-I-L-I, and I get military. And here you can see a rather large Cold War buildup in the military after World War II. So one of the reasons I wanted to point this out, though, is you notice that there's some deal of conversation on the right here about this topic. Now let's say I click this. So I clicked it, this website updates. So my query is actually now military with a capital M, the full word. But you see I still have the same commentary. And the issue here is that different parameterizations of the visualization can actually still lead to the same state. So in this case, two different queries still had the same result set. So if we relied on the parameters of a visualization alone to tie to commentary, we'd have a huge opportunity for crosstalk or missed collaboration. So what we do is behind the scenes, we actually take the query result set, index that, and use that to generate a key by which we tie collaborative commentary to the visualization, and thus hopefully reduce the potential for crosstalk within the system. Now I'd like to show you one more example, and that's waiter. And the reason I like waiter is because it shows a potential weakness in this type of visual representation. So here I'm using stacked time series, so each entry is stacked on top of each other. And this is good for showing aggregate patterns, but sometimes makes it difficult to see the trends of an individual data point. So it may be difficult to notice, for instance, that if I filter to just men, there's actually a large dip around the second half of the last century. So this is interesting. Maybe we want to make a comment on this. Why the dip in males? So we can be conscientious and even point to the trend that we care about to make it clear. So any hypotheses on why this might be? Don't be shy. Military, so there's wars. So that includes, let's see, World War II in this time, Korea, Vietnam, which had a draft, of course. Any other thoughts?
Maybe they started calling themselves something else.
Okay, change in name. Yeah, did fast food affect this? Oops, can't type. So one other possibility that's been floated in other talks is what they called feminization. Like, did the perceived gender role of the job change? Because that also might coincide with the large influx of women that we saw earlier. But if that were the case, it begs the question then, why is there a subsequent rise in males afterwards? But we can leave those questions behind for now. So perhaps I might want to revisit this question later or share it with someone else. I can also collect views of interest in bookmarks. So I can use this to create tours through multiple views that weave a story through multiple parts of the data, or allow me to revisit views of interest. So for example, I might go back to this overview of waiters, create a new comment, and create a signpost. Say, don't miss the dip in males. Oops. Here. So then I can grab my view, drop it in here. I won't edit the link text for brevity. But then here's a signpost in the data so that people might know, oh, there's some interesting trend if I've arrived here. And so all of these features have been placed in the context of visualization. The data is front and center. But of course, we can look at other aspects as well, including searchable listings of all the comments that others have left behind that maybe give us a sense more richly of how others have explored the data. And since we're here at Washington, maybe we'll see what's up with disappearing professors. And so here we see a comment pointing out that how the Census Bureau categorizes data may have changed over time. So at one point we have subdivision into things like professor of engineering, medical, mathematics, physics, psychology, science, etc. But by the time you get to 2000, everyone again has been subsumed by this general category. So here we're seeing some noise in the data, which is like shift in schematization over the years. So now I'll jump back to the slides. So that was just one example. There are many other visualizations we place within this site. And so if you want examples, you can come see me afterwards. They're pretty fun to play with. But now I'd like to review some of the design decisions we made in building this site. And so this was intentionally an exploratory design. We built this to put it out there and really see how people took advantage of these collaborative features and use this to seed iterative design of additional techniques into the future. One thing we wanted to support was sharing, both within the visualization and across the web. So we provided these updating links as well as tying commentary directly to different states of the visualization. We knew that pointing at interesting trends and outliers would likely be important, but we didn't want to overly constrain that process, so we first provided just these free-form drawing tools so we could then observe usage. We knew that telling stories and looking at multiple views would be important, and while there's more our system could do, we wanted to at least provide a minimum amount of support for that, so we provided this collecting and linking mechanism. We also wanted to support awareness of social activity, including through the searchable comment listings, but also it's why we tied a collaborative commentary to particular views and put it on the side rather than below the fold, so as people explored, the comments would pop up where people would be sure to catch them. But in doing so, we wanted to follow a rule within computer-supported cooperative work, which is, as you add collaborative features, don't disrupt the single-user case. So this is why you turn on annotations by choice as opposed to seeing a screen plastered with them, so that people could engage with the social features as they wanted to, but if they just wanted to dive through the data on their own, they should be able to do that as well. So then given this rationale, we then wanted to understand how was this affecting usage. So we ran a set of user studies. And this included a 30-participant laboratory study in which people came in and did 25-minute usage sessions and with a think aloud protocol. We also did a live deployment within the IBM intranet in which any employee could use the system using their existing intranet account. And so from these different studies, we got 12.5 hours of qualitative observation from the lab studies, as well as 258 comments, as well as rich usage sessions because we instrumented everything in the site. And so one of the things we did to analyze this data was run a formal content analysis. And so what this involved is that we came up with a coding rubric that was iteratively developed amongst myself and my collaborators. Then we each independently coded the data and ran inter-rater reliability statistics to make sure our judgments were in accordance with each other. And the result is these overlapping labels that try and tag the role of different comments within the system. So not surprisingly, most comments had to do with observations of the data. This was about 81%. And these were highly coupled with people asking questions, as in why is the data the way it is, or forming hypotheses as potential explanations for the trend they see. But also interestingly, 15.7% of all comments also involve data integrity. So people engaged in verification and cleaning tasks, and often, like I said, putting signposts in the data to help others interpret it, perhaps, and be more skeptical of what they're seeing. Now here's some qualitative examples of some of the comments we saw. One was someone interested in the military, so we started annotating a timeline of wars, which he thought might have affected military buildup. Another user thought the economy was important, but also built on top of this timeline, which you see is missing a label. Someone else came in, flushed it out, and built on top of the previous work. Other people tried to inject some humor into their observations. So the comment here said the Great Depression killed a lot of brokers, and conveniently had the suicidal broker jumping right into the valley of the Great Depression. Though when I saw this chart, the first thing that jumped out to me was like, man, there's a lot of stockbrokers after 1970. But the most interesting examples were those involving collaborative sense-making. So here was a comment that asked, where did the dentist go? There was a peak around 1930, so then why did the percentage of dentists drop off? So some people suggested that maybe it's because we started adding fluoride to the water about that point, so maybe our teeth got better. But why the bump? And this elicited different types of evidence ranging from database stuff, like facts such as the introduction of fluoride, to speculation such as, my kids go to the dentist twice a year, but I only, went once, so maybe that has to do with the bump. But other people thought a little more systematically and said, well, let's zoom out. Here's a view where someone combined dentists with technicians, medical and dental, and made the argument that perhaps what we're really seeing is a rise in dentistry tied to a stratification of the labor force. So here, more and more hygienists are coming into work, making dentistry more specialized, so you need fewer of them. And then other people piled on with other pieces of evidence, such as my brother went to dental school and the costs are rising each year, so maybe that corroborates this. Now, so those are some examples. We also analyzed different parts of usage, including how people used annotations. And the big takeaway here was that 39%, or about 4 in 10 comments, included annotations. The vast majority of them were pointing to very specific points, trends, or regions. And so this had some interesting implications, one in terms of how we might make more structured forms of annotation. And interestingly, this also is in accordance with findings from social psychology, such as the work of Herb Clark at Stanford, who looks at how humans engage in pointing and reference. And for example, we found behaviors like that where people use ambiguous references like this trend or that spike, and then use annotations to disambiguate what they're saying. We also looked at navigation patterns, that is how people arrived at particular views. And the big finding here was that our view indexing technique really aided conversation. So by indexing the state of the view and using that to tie to collaboration, it's very helpful. And I say this because 14.2% of views were reached via multiple parameter settings. But of all visits, 28.3% of all visits were to these multiply parameterized views. So if we didn't do this indexing, people would have missed conversation. And for those of you who study social computing, you won't be surprised to learn that visits and comments both exhibited a power law distribution. So I'd like to share with you one final qualitative observation that we had, which was the complementary faces of usage that all users exhibited. And we called this Voyagers and Voyeurs. So as people came to the system, they often started as what we called a Voyager. They were focused on the visualized data and often used themselves in their immediate social context as a query generation technique. So people would search for their jobs or the jobs of their friends and family and start getting some coverage of the data based on their local knowledge. Eventually, they'd get tired of this or run out of questions, and then instead of leaving the site, we find that they would transition into looking at the comment listings themselves. And that's when we called them voyeurs. And this came from a quote from a participant who said, "I feel like a data voyeur. I love looking at what other people have been searching for." And so while some people did this to kind of get a sense of what the crowd was interested in or look for people they knew and hypothesize about what interest they might have, one of the interesting insights that I took from this was that in every case, people found new topics they hadn't thought of that sparked their interest and catalyzed new exploration. So people would link in from a comment, jump back into the visualization, and start exploring anew. So providing these traces of social activity helped catalyze additional exploration within the visualization. And so we found these findings very encouraging. They kind of replicated some of our previous findings in a more structured format and points the way to a new research area that we've been exploring, which we call social data analysis. So we've fortunately been able to raise a lot of interest in this concept at the most recent Information Visualization Conference. We're also co-organizing a workshop on the topic at CHI 2008 this year. But fortunately, we're not the only ones who are interested in it. So for example, some of you may be familiar with this guy, Hans Rosling of the Gapminder Foundation, who uses interactive visualizations to communicate global economic development statistics. And so Hans has done a great service to the rest of us in that not only has he brought attention to interactive visualization, he's highlighted its value as a storytelling medium for really using it to communicate findings to others. And now other notable folks have shown that if you communicate well enough with data graphics, they may even give you a Nobel Prize. Now, Silicon Valley has been getting in on the act too. This is Swivel.com, a startup down in the valley, which allows people to upload data sets that then become publicly available, tied them to static visualizations, which then can have comments and rankings attached to them. And partially furthered on by our success with the Census system, my colleagues at IBM Research have also released another website, manyeyes.com, which similarly to Swivel allows you to upload data sets and tie them to visualizations, but in this case, a much richer palette of visualizations that afford a bit more exploration. However, I have to say, both of these sites, however, don't provide the same richness of collaborative features that we explored in Census. And more importantly, those features themselves were just a first step in a much larger space that I would like to explore. So in the remainder of this talk, I'd like to cover just a few of the interesting research questions I'd like to look into going forward. And so one of those questions is, how can users' activity traces be used to improve collaborative analysis? I've already given you this example of Voyagers and Voyeurs, but how else can we leverage collected activity data? So we ran one actually very simple exercise in this area. There's many more we could do. This was a project we called Scented Widgets. And no, you can't smell them, but the name comes from the notion of information scent, which comes from information foraging theory, which is the study of the cues that we use to navigate information spaces. And our idea was, if we just simply surface activity data, how might this change analysis patterns? So what you see on the left here is a navigation widget that lists different occupations within the census data. And these bar charts just show the amount of visitation data to those different views collected from our studies of census. So we ran a controlled experiment where we presented this interface to users and found that, not surprisingly, showing this activity data leads users to preferentially revisit popular views more often. But also, and perhaps more interestingly, by showing where people haven't gone, it actually increased the number of unique observations people were making as they would allocate themselves to views that haven't been seen yet. Now, another question is, how should annotation techniques be designed to provide nuanced pointing behaviors? So for example, in Census, we had this geometric, graphical form of annotation. However, this is somewhat limiting is that it only works on these particular views of the data. Now, there's other things we might do that are a little more formalized and metric, so we might actually tie this to underlying data. And so is there a dichotomy between these free-form graphical annotations and then these more structured forms of data-aware annotations? And could we devise maybe new interface techniques that more fluidly bridges between these two worlds? So in the meantime, we've built systems for doing what we call data-aware annotation. This is a visualization built in the FLAIR toolkit that shows crime statistics, homicide data from Los Angeles County in 2007. And so this map shows the location here geographically of where homicides occurred and other things such as the cause of death or the ethnicity of victims. And as I select different regions here, I highlight them. You might see down here there's actually a query clause that highlights. So what I'm doing is I'm actually taking these annotations and tying them to declarative database queries over the underlying data set. So for example, I might highlight East LA, and I'm actually tied to a range query of latitude and longitude underneath. So for example, I might make a new comment about East LA, and I save the query along with the commentary. I can do this and view other annotations people might have left. So for example, I'll look at here, East LA again. Now, one of the advantages of doing this is that I can then repurpose the annotation across different visual representations. This is a geographic view, but I might change that to instead show a timeline on the x-axis and here the age of victims along the y-axis. And because I know the declarative structure of the annotation, I can actually retarget query terms to new interface widgets and then perhaps build up, either evaluate how that looks under a change of representation or iteratively refine or expand my query as I go through the data. So for example, I might then transition to a histogram view that shows counts per month. And then one last question I want to share is, how can diverse collaborative contributions be better integrated to improve the scalability of these types of sites? So a common problem for user-generated content sites is how to synthesize all the contributions of different users. So for example, Wikipedia allows people to revise the same article, as well as keeping a revision system that allows you to backtrack when vandalism occurs. Other systems such as NASA ClickWorkers use statistics. So in this service, users come to the site and click along the outlines of craters on these images, and then statistics can be run to try and infer for the NASA folks where the crater boundaries are, saving them a lot of work. So the analogous question is, how could we structure conversation within analysis environments to help synthesize contribution? Perhaps by formalizing notions of question, hypothesis, and evidence, or providing certain types of scoring and ranking functions, we can get better types of statistical and other forms of aggregation, while maybe also introducing gameplay mechanisms to help bias people towards what we might consider better analytical practice. And so, in exploring these and other questions, I'd like to use concrete applications to drive the research forward. And so just one example that we've started to look at already is statistics education. So a recent report from educational psychologists notes a number of opportunities for advancing how statistics are taught, including emphasizing data exploration over just rote application of statistical formulae, and investigating real-life problems, engaging in data analysis, supporting collaboration and student involvement. So we've just submitted an NSF proposal in partnership with CalTeach, a group at Berkeley that teaches undergrads to become math and science teachers. And we hope to develop our technology in accordance with curricula, and we're collaborating with AP statistics teachers at Berkeley High to help develop, use visualization techniques to teach data analysis and statistical concepts. So now, I'd like to conclude my talk by just quickly reviewing some of the contributions of the work I've shared with you today. So my work in visualization techniques has introduced new algorithms for optimized data displays and new visual analysis tools. And in future work, I'd like to continue to develop techniques for new and more complicated forms of data, as well as explore the space of semi and fully automated design tools for creating visualizations. My work in visualization tools has introduced two different toolkits that simplify the process of creating and customizing visualizations and have led to real-world impact in both research and academia. But one limitation is that they focus primarily on programmers, and so I'm interested in extending this to designers and tools for end users to create their own rich visualizations in a data-centric manner. And finally, I've introduced new systems and techniques for social data analysis, including a preliminary characterization of social data analysis patterns. In the future, I want to continue to explore this area, create new analysis environments, and more fully answer some of the questions I shared with you today. And again, this is all in service of a greater goal. The overarching intellectual aim is to improve our abilities as humans to analyze and communicate information. Yes?
What is the impact on your techniques of having synchronous versus asynchronous collaboration, and then in particular for synchronous of having sort of big display walls where you've got groups of people pointing at it versus people working on their own desktops? Would you imagine quite different kinds of technologies, or do these all marry?
So the question is, how do basically interaction or collaborative patterns change based on the medium and also the kind of temporal dimension of the collaboration? So there's things you can do in co-located collaborative communication that you can't do in asynchronous, and vice versa. So there are differences. For example, when I was observing people use the visitor social network thing together, people point to things and they engage in conversation. I think one of the things that was useful was that it was easier to scale up the conversation up to a point. That is, people could interrupt each other and engage each other. So some interesting conversational dynamics, I think, might be more difficult in an asynchronous manner. But there's other things, and this has been more the focus of the research I've been looking at. In asynchronous, you have some other additional possibilities. Not only the fact that people are collaborating over time, so they don't have to be there at the same place, but also allows some things that I would like to explore in terms of it's easier to manage some private-public differences. Like people could work on their own, at their own desktop, maybe working with evidence, creating a visualization, and then share it when they're ready. So there's certain things we've thought of that weren't in Census, but we thought of subsequently of people basically working on analysis trails and saving views, building that up, and then releasing that later. And so I could go on for days. There's like lots of other interest things we can flesh out. So I'd say, is there a more specific aspect that you're curious about, or?
I'll talk to you at dinner about it. Yes.
Well, let's talk at dinner. Absolutely. Thank you. Jake.
Do you think that, again, following the same thread, that like multiple devices where there's sort of shared private and public, kind of like a wall display or multiple small devices, et cetera, is there opportunities where that adds something, beyond the sum of its parts, kind of to this?
Right. So does adding multiple devices, which may go across different media and scales, add something to this equation? I think absolutely it can. I mean, along with similarly, in the same scenario I just described, previously. I think there's interesting things that for wall size displays too. How do people use it at the same time? But that's obviously of a slightly different nature than the work I've presented here.
Okay, last question.
Okay.
So one of the things that people do with large amounts of it is build models of them. And then it's difficult to visualize the models.
Mm-hmm.
Right? And you had one example of that here, which was clustering.
Yes.
Right? But you just did a fairly standard, moving through the hierarchy.
Mm-hmm.
Do you have any other thoughts or interests in terms of visualizing models as opposed to the raw data?
So yeah, the question is, I have interest in visualizing models in addition to the raw data. Absolutely. So I mean, the one example I showed was of clustering output. So it's not something I've worked on yet, but a future research trend I'm very interested in is a deeper marriage of visualization technologies in both statistical modeling or data mining techniques. And there's lots of ways in which that can arise. So one is in this visualizing both the process and output of automated techniques to make them both understandable and accountable to people using them. There's also potentially even allowing human-in-the-loop type data analysis where people author patterns, then you can reapply those patterns automatically, visualize the results across a large data set, time streams that might have repeated patterns such as video and audio data or other types of, like, say, neuro recordings. Maybe good examples to explore that further. And I've had interesting conversations along these lines with people. I think adding an analytics along with visualization is very important, future direction. And even if we get perfect analytics, we still need good visualizations at the end of that pipeline so that people can make sense of the outputs.
Okay, thank you. Please come down.
Thank you.